Hello, my name's Lee Kerley and I work at Sony Pictures ImageWorks. Today, I'm going to be talking about how we put these physically based pieces together to create materials and tools for artists to use in production. I've worked on one or two Spider-Man movies through the years, and at least 3 of them were made using the technology I'm going to show you today. I want to start out by telling you what we're not going to talk about today. There'll be no discussion of using correct units, no mention of BXDFs or sampling. At ImageWorks, a lot of these things are handled inside the renderer and exposed in OSL as closures. These were discussed in the 2017 edition of this course by Chris Coller and Alejandro Contri, as well as in the earlier presentation in 2012 by Adam Martinez. The OSL shaders are responsible for putting together these building blocks and delivering the renderer a description of the material. A closure in OSL is a description of the BXDF that is then interpreted and implemented by the renderer. The current set of closures used by the shaders has been really stable over the past 5 years since we introduced the latest generation of the shader library at ImageWorks. The coating closures accept the closure beneath as arguments, so the renderer can appropriately compensate for energy absorbed or reflected by these coatings. The standard closure incorporates a diffuse model, 2 GGX specular lobes, and our metallic model, with blending weights provided to maintain energy conservation internally. My mental model for the standard closure is that it handles all the things that can happen on the outside of the surface, and conversely, the dielectric closure handles the things that happen on the inside of the surface, so anything that's refractive, like glass, volumetric, or subsurface. The dielectric has a thin and solid mode, which we'll hear more about later. The selection of these closures was largely motivated by the choices we make about being strict when blending materials. What we are going to talk about today is how we put those pieces together and how they are presented to the artist in a friendly yet powerful way, allowing them the creative power to experiment quickly while at the same time staying mostly within the bounds of physical correctness. I'll show some of the tools we built and also talk about how we hide away much of the energy conservation concerns from the artist in the tooling so they can't break the rules too much. In contrast to the previous MaterialX presentation that included vertical and horizontal layering at the granularity of the BXDF, we have a fixed vertical layering strategy for the composition of the closures and instead perform a horizontal layering at the granularity of entire materials with OSL and Katana tools that we've developed. Finally, I'll talk a little bit about the technical specifics about how we blend the Double GGX Lobes in a way that tries to maximize the preservation of the original artist's intent, and a few other tricks we learned along the way. What do I mean when I say material? At ImageWorks, we've always presented look-driven lighting artists with a monolithic material interface. This has proven particularly useful as shading technology changed, including the adoption of physically based shading, as it allows us to evolve the technology beneath a familiar interface. This eases the burden for retraining and makes adoption of new technology easier to roll out. For a long time, we had a large library of different materials with automatic texturing and some basic procedural support built in, but as shows needed increasing levels of visual complexity, there was more call for custom shader development on each show, and it was clear the team couldn't scale in response to the work that was needed. About 7 years ago, we introduced a tool called Pattern Create that allowed artists to be able to use a node graph-based approach to texture the inputs of the materials with patterns. All of the pattern nodes are authored by the shading team in OSL and delivered to the artist in the form of a library. This allowed a lot of the bespoke production development to be completed by technical TDs, while allowing less technical artists to be able to interact with the material system without feeling overwhelmed. In the latest generation of the Shade Library, we provide artists a small set of base materials to start working from. These are built from closure building blocks provided by Arnold in OSL. The glass and general materials are 2 that use the dielectric closure, so they have a volumetric component to them. We use 2 different versions of each of these that can be used depending on how the asset is modeled, which we'll see on the next slide. The artist then used these materials in combination with Pattern Create to create rich material hierarchies inside a katana. As I mentioned, we have the idea of thickness as a differentiator between materials in the system. Here we can see 2 models, a single polyplane and a box. We use the thin version of the volumetric shading component for the single polyplane and the solid version for the box. The thin version simulates the thickness of the material model, and the 2 versions appear visually similar when used with the correct geometry. Here we've dialed the thickness parameter of the thin model to the actual thickness of the box geometry so their appearances match. For the materials that don't model any volumetric effect, the thickness model is irrelevant, and we call these auto because they can automatically adopt the thickness model of any other material that they're combined with. Nearly all the other material parameters are floating point, and so they can just be interpolated, but the thickness model is a geometric decision. This is why we decided to introduce the separation here, so it isn't possible to end up accidentally mixing the two or using the wrong model on the wrong geometry. Here we wedge the thickness parameter of the thin material to match the geometric thickness of the solid material. Their appearances will approximately match. When we simulate the thickness in the thin material, we ignore the effects of ray bending due to the IOR at median boundaries. This is generally okay because we tend to use this only for things that would be relatively thin if they were modeled as solid objects. A material provides both the surface and displacement shader to the renderer, but the user is not aware of the two separate pieces because it's presented as a single monolithic interface. The materials themselves are a small network of OSL nodes, and they all have a very similar topology, and here we can see a slightly simplified example. The params node is the only node that differs per base material as it provides the material-specific logic. The central root node defines the material elements that are common to all materials, such as coatings and AOVs, and the surf and disk root nodes are responsible for taking the accumulated material data and constructing the surface and displacement shader outputs that the renderer expects. The connections in this network are the UberData struct, which we'll see next. The UberData struct is the heart of the system, and it's actually a struct of structs. Each substruct represents one of the illumination building blocks in the system and contains the necessary data to represent that component to the renderer. Loosely, the members of these structs map to the parameters in the closure, although this isn't always strictly true. There are times when we can derive some closure parameters from multiple members in the struct, or other times when we reuse a closure to represent a simpler struct, so the number of parameters of the closure can have defaults that aren't captured in the substruct. For example, our standard closure actually contains our plastic and metal model, but we choose to separate these in the struct to allow for better blending later on. Each substruct has its own weight, which controls how much of that substruct will eventually be present in the material. These weights are controlled by inputs from the artists, but logic in the OSL params node ensures that the weights always sum to 1 for the illumination substructs. And the substructs are independent from each other. Each component might have its own copy of surface normal, roughness, or color parameters. This becomes really important when we start thinking about combining these materials together, and we want to make sure that some of these parameters don't pollute each other when blending. We can see here a small collection of materials artists created these base materials with Pattern Create. Shows will often create, or steal from another show, a large set of these materials to create a material library to start from. A lot of asset load dev can be completed using materials from these libraries, but from time to time there can be a need to combine more than one material together to complete an asset. Maybe the shape has been modeled such that two logically different components has been combined into a single mesh. Perhaps the handle and a blade of a knife were merged, and we want a wood handle and a metal blade. Or sometimes artists just need to separate out the material into different logical blocks for easier dialing. Here we have a contrived, non-production example where a wooden asset is being covered in gold spots. We need a single material we can assign to the shape that incorporates both sets of properties. In the previous version of the shader library, we would sometimes find that artists would reach for Pattern Create to perform the combining of materials. This approach is effectively artist-created parameter blending. Here we see an overly complicated pattern graph where really the only interesting blend logic is the yellow backdrop at the bottom. This approach is quite labor intensive and easy to make mistakes, and it also clutters up the pattern graph. What we need is a node-based tool, but for whole materials, and that's how we ended up with MaterialCombine. MaterialCombine is a node-based material blending system. Because the system is built on top of the same technology as Pattern Create, we get to reuse the pattern nodes we already have. It's not strictly a parameter blending system, as we don't blend the input parameters to the materials, but instead we blend the contents of the UberData struct. We built a small library of combine nodes that allow the blended material to be manipulated in more interesting ways than just over. Getting back to our example from before, we see the corresponding MaterialCombine graph that creates the identical image. The green nodes here represent entire materials, and we end up with a system that's much simpler and easier for the artist to comprehend. This means they're now able to craft much more complex combined materials. The blend node is the heart of the entire system and provides a simple linear blend between two materials. It turns out that simple linear blend isn't quite as simple as it first seems, but I'll get to that in a slide or two. But this node is really the workhorse of MaterialCombine. We also have a slightly more familiar over node that just uses the existence of the foreground layer to drive the mix of the blend node, and other combine nodes that allow artists to blend in, completely replace or redefine subcomponents in the UberData struct. Replace sheen, for example, was proven useful for adding dust to the tops of materials really easily. Or we also often see artists stealing the displacement component from one base material and reusing it in a more complex combined surface material component. We mentioned before that some of the materials are intended to be used with geometry that's modeled as a single surface and others with geometry that's been modeled with an interior volume. A combined material is still a single material, so it needs to have a single thickness model. Consequently, the tools enforce that thin materials cannot be blended with solid and vice versa, and the materials that don't have a thickness model, such as emission or plastic metal, are allowed to be combined with anything. The tools automatically derive the appropriate thickness model based on the input materials that are used in the graph. Next, to talk a little about the mechanics of how we connect the materials. Remember that the materials all share a common node graph topology. Here we see a MaterialCombine graph, and to connect the material layers, we slice that material topology in half and just keep the first part. We reuse the last part for the output, since we need to end up with one surface and one displacement shader. This allows us to use a common set of nodes to deliver the closures to the renderer, no matter if the material is a simple single layer material or a combined material. Both Pattern Create and MaterialCombine exist within Katana, which is a node-based look development and lighting package. This affords the artist a large amount of power over and above the operations on a single material location. Materials are authored in a tree hierarchy where child materials inherit their parent material configurations, allowing for sparse edits to create entirely new materials to be used. A new material can be created, its patterns or material graph created or modified at any point in the Katana node graph. This means that the data can also be inspected at any point in the node graph as well. Also, any parameter of any pattern, material layer inside of MaterialCombine can be overridden for any geometry location independent of the material assigned to that location. For example, it's really easy for artists to override overall displacement scale to 0.5 for large ports they're seen to scale the displacement down in a single edit. As I said earlier, the blend node is really the heart of the entire combining system. We don't blend the input parameters on the materials, but we blend the contents of the UberData struct. When we blend materials, we need to take care that data from one component does not pollute another as we blend the two materials together. We also need to make sure that we're balancing the weights of each of the building blocks to maintain energy conservation. And then finally, I'll talk a little bit about a trick we do with our Double GGX Lobe that means that when we blend, most of the time we can do a lot better than the naive approach of a linear blend. Within the UberData struct, each substruct is independent from the others. Some parameters like color or surface normal are repeated in several substructs. This means we can blend those structs without incorrect cross-pollination of data. Here we see an example where we're blending a red plastic with a green metal. The top example demonstrates what happens when we don't separate the color in the metal and the plastic substructs. You can see that once we get to the middle of the blend, the color looks like neither of the original colors. We get a polluted color because we've just done a simple linear blend between the two colors. Below, we see that if we keep the metal color and plastic color separate, this gives us a material with a more pleasing color at the midpoint. This is because by duplicating the color in each component, we now just need to blend the weights of those components. We just mix from being plastic to metal, but the plastic can stay red for the entire blend. We'll see more on this weighted mixing next. We're going to look at a simplified example of how we blend different components of the UberData struct using their weights. We're just going to consider a material that can be metal or plastic, two components which are separate structs in our model, and at the end they are just linearly summed to get the result. This is possible because the system ensures that the sums of these weights never exceeds 1. Here we can see that the red plastic material has a plastic weight of 1 and a plastic color of red, but the metallic component has a weight of 0 and a color of black, the default, because the artist never made a choice here. The green metal is the complement of this, with a plastic weight of 0 and a metal weight of 1 and no plastic color specified. And we can see on the right the final summed up material. Now we're going to blend these two materials together using a blend amount x. If we carry out a straightforward linear blend of the values using x, then we know that we have the correct results at x equals 1 and x equals 0. But what do we have in the middle? We'd like it to look something like this. But linearly interpolating the weight and the color leads to a result here that is darker than we'd expect it to be. So instead we use weighted mixing to do it a little better. The crux of the weighted mixing is the wmix function. You can see here that the amount we take from A or B is not only affected by the overall blending weight x, but also by the weights of the respective sides as well. We have a few early out cases for optimization. These optimizations also make it easier to understand the goals of the function. If the weights on both sides are the same, then the regular linear interpolation is good. Or if either side has a weight of 0, then we just want to use everything from the other side. The generalized formula below is just a continuous version of these optimizations, and basically says use more of the side that you have a higher weight for. Once we have the wmix function for our substruct, then in most cases we just perform a linear blend between the two using this newly calculated weight. But there are a few special cases that I'll touch on in a minute. It might look like we have a long series of conditionals, but the runtime optimization inside of OSL will often optimize these away. In fact, the runtime optimization in OSL is one of the key pieces of technology we needed to allow artists the freedom to author their own node graphs. We often see a reduction in the order of 90 to 95% of the instructions in the shader, and without that we would end up with very large materials that would be too expensive to evaluate. Concretely, what that means in our simple blending case is that when we're blending the plastic component for 0.5, we keep the original red plastic color. This is because the plastic weight of the green metal material is 0, and so our wmix value just selects all of A. We just keep all of the plastic component data untouched and only linearly blend the weight. This gives us the result we want, which in this situation is exactly correct. In other more complex real-world solutions, the blend falls as close to the correct solution as we can get by blending. We have two GGX lobes in our model because it allows us to achieve a more complex specular profiles without introducing more complex models. The two lobes are just linearly blended, so we're always energy conserving. Here I have a sharp spec at roughness 0.1, and then another broad spec at roughness 0.5. With two spec lobes I can blend these two and retain my tight spec and still have a sense of the hazy spec underneath, but if we only had one spec lobe, we'd have to find some poor compromise, like here at roughness 0.3. This was covered in a lot more detail by Chris Culler in the 2017 course. One of the cases we can do better than a simple linear blend of the data inside the substructs is with our GGX lobes. Our shading model has two GGX lobes, so we have two roughness values and a 0 to 1 blend between the two lobes in each material. If we have two input materials A and B that are being blended and have computed a wmix value x, then there are 4 lobes in total to consider. We need to reduce this to 2 final output GGX lobes. There are 3 different ways we can pair up these 4 lobes to make 2 final lobes. Option 1, blending the 2 lobes from A to create the first output lobe, and then the 2 lobes from B to create the second output lobe. Option 2, blending the 2 first lobes from A and B to create the first output lobe, and then the second 2 from an A and B to create the second. And option 3, crossing both the lobes in the materials to create the output lobes. So now we have the options, we just need to pick which of these 3 combinations is best. We have a simple example here where X is the wmix between material A and material B, and AR blend and BR blend are the mixing factors within the materials of the 2 GGX lobes. To select which one of these 3 permutations is best, we start by quantifying how much of each of these input lobes we have, by using X and the 2 R blend values. By visualizing this, we can intuit that we'd like to end up with a mix that prioritizes retaining A1 and B2 as separate lobes, as they appear to be dominant. Next, we calculate the quality of each of the options by measuring the error introduced. The cost of each lobe is calculated by considering the difference between the roughness of the 2 input lobes that contribute to it, and then the overall cost is the sum of these costs scaled by how much of each lobe exists. Once we've calculated the cost for all 3 options, then we can choose the option with the lowest cost and we know which combination to use. Once we've made the decision, we blend the 2 lobes together using a familiar wmix weighting approach, but this time using the quantities of each lobe that we calculated earlier. This is a bit of a simplification, as our actual implementation of the cost function also incorporates the specular tint and attempts to consider anisotropy changes as well. Just to run through a quick concrete example to make this a little clearer. Here we have 2 materials. Notice that on the A side we have an R blend of 0, which means we're only using one of the GGX lobes. We're going to blend these 2 materials with a blend amount of 0.4, which means using the quantity values for each of the lobes and the cost functions from the previous slide, we can calculate the cost of each of the 3 options. On the A side, QA2 is 0 because we're only using one of the lobes, so this means that the cost of the side that includes that lobe on each option will always be 0. The differences here are subtle, but hopefully you can see that the lowest cost option here, option 1, is the one that retains the original tight spec that is dominant on the side that we're blending from. Other gotchas where we do a little more than just a simple linear blend include index of refraction, where we found that linearly blending the reflectance instead of IOR directly gave much better results, so we convert the IOR values, do the blend, and then convert back. We also cannot just linearly interpolate the normals, otherwise we might not have a unit length vector. We considered a spherical LUT, but we found that if we took a little care with the directions of the vectors, then we could just do a simple linear interpolation and renormalize afterwards, which saved us a bunch of trigonometry. Because of how the data is structured, we're nearly always blending 2 normals on the same side of the surface, so the LUT plus normalization works well enough. Probably the biggest lesson we learned was the logic we use needs to always be continuous. Artists quickly stumble across discontinuities if they exist, so while we strive to find the best ways to combine things, we would work harder to find ways that there would not be any discontinuities across the blend region. Today we've seen both the roughness blending and the wmix function as examples of this continuousness. As far as next steps or future work goes, there's always more we can do. We regularly have requests for more nodes in the system, and it's often a balancing act between just saying yes and weighing the cost of increased cognitive load on users for the larger library of nodes. And there's always work to be done on the graph-based tools themselves. We do try a little to account for the error introduced by anisotropy changes when blending the double GGX lobes, but there's definitely room for improvement here. And the other piece of work that's on the horizon is to work on merging some of those materials that are presented separately to the user to more of an Uber shader model. This isn't so much to make up for a shortcoming in the system as it is in response to some of the awkwardness that Katana imposes on how the data is stored and the ability to reorganize data in a more dynamic way. And that about wraps it up. Today, hopefully I've given you an overview of how we put the physically based shading pieces together at ImageWorks. The system I presented has been in use for the past 5 years on a wide range of animated feature and visual effects shows. This has been the longest running shader library generation at my time at ImageWorks, and I think that's because we found a good balance between keeping things on Rails to create realistic physically based images while also keeping the flexibility to explore creative ideas. Thank you for your time listening to this presentation, and thank you for the course organizers for inviting me. Finally, I would like to extend a special thank you to all the people mentioned here whose hard work has made all this happen. After all, it takes a village to raise a shader library.